Dear students, hello. In this video, we are going to study two exercises related to limits of trigonometric functions. These two exercises test your understanding of trigonometric equivalence near zero. Sine of u is equivalent to u, tangent of u is equivalent to u, and your ability to identify the dominant terms. They also require you to apply simple trigonometric identities and the Squeeze theorem when a function is bounded. Exercise 1. Calculate the following limit, using the equivalence of the rate of change of sine of u as u approaches 0. That is, the limit as u approaches 0 of sine of u divided by u equals 1. The limit as x approaches 0 of sine squared of 7 times x plus 3 times tangent of 3 times x squared, all divided by 8 times x squared. Exercise 2. 1. Calculate the limit L1 defined as follows. L1 is equal to the limit as x approaches 0 of 1 minus cosine of 3 times x divided by x times sine of x. Hint. Use the formula 1 minus cosine of a is equal to 2 times sine squared of a over 2. Then recall that the limit as x approaches 0 of sine of x divided by x is equal to 1. 2. Calculate the limit L2 defined as follows. L2 is equal to the limit as x approaches 0 of tangent squared of 2 times x plus sine squared of 5 times x, all divided by x squared. Hint. Break down the fraction and apply the following limits. The limit as x approaches 0 of tangent of a times x divided by x is equal to a. The limit as x approaches 0 of sine of a times x divided by x is equal to a. 3. Let the function f of x be equal to x squared minus 5 times sine of x, all divided by x squared plus 1. Calculate the limit L3 defined as follows. L3 is equal to the limit as x approaches positive infinity of f of x. Hint. Bound the sine function between -1 and +1. Then apply the Squeeze theorem. Solution. Exercise 1. Statement of the exercise. We are asked to compute the limit as the variable x approaches 0 of the following expression. Sine squared of 7 times x plus 3 times the tangent of 3 times x squared, all divided by 8 times x squared. A good reaction when facing this kind of expression is to recognize that it is an indeterminate quotient of the form 0 over 0. That tells us to transform and simplify using the standard remarkable limits every student should master. First remarkable limit. As the variable u approaches 0, sine of u divided by u tends to 1. Second remarkable limit. As the variable u approaches 0, tangent of u divided by u also tends to 1. Teacher's tip. Memorize these two remarkable limits. They are the keys to almost every limit problem that involves sine or tangent. Rewriting the fraction. To use these remarkable limits effectively, we first rewrite our fraction in order to highlight the classical ratios, sine of something over that something, or tangent of something over that something. So we write the limit as x approaches 0 of 1/8 multiplied by the sum of two terms. The first term is the square of sine of 7x over x. The second term is 3 times tangent of 3x squared divided by x squared. This step is essential. It makes the remarkable limits appear clearly. Study of the first term. Let us first consider the ratio sine of 7x over x. As x approaches 0, this ratio is equivalent to 7. Indeed, sine of 7x over 7x tends to 1, which means sine of 7x over x is equivalent to 7. Since our term is squared, we get 7 squared, that is 49. Pedagogical reminder: do not confuse sine of x over x with sine of ax over x. In the second case, remember that sine of ax over ax tends to 1, but since the denominator is only x, a factor of a remains. Study of the second term. Now let us look at tangent of 3x squared divided by x squared. We rewrite this as tangent of 3x squared over 3x squared multiplied by 3. As x approaches 0, the ratio tangent of 3x squared over 3x squared tends to 1, so the whole expression is equivalent to 3. Then we multiply by the coefficient already present in front, namely 3. We therefore obtain 9. Exercise 2. First question. Calculation of limit L1. We are asked to determine the limit as x approaches 0 of the following expression. The numerator is 1 minus cosine of 3x, and the denominator is x times sine of x. As x approaches 0, cosine of 3x tends to 1, and sine of x tends to 0. This gives an indeterminate form of type 0 over 0. Pedagogical reminder: in this type of situation, you must use the remarkable limits. Two fundamental results must be known and applied. First, as x approaches 0, sine of x over x tends to 1. Second, the useful trigonometric identity here is 1 minus cosine of a equals 2 times sine squared of a over 2. Applying this identity to our problem, L1 equals the limit as x approaches 0 of 2 times sine squared of 3x over 2 divided by x times sine of x. We rewrite this fraction in order to use the remarkable limit. We obtain 2 multiplied by sine of 3x over 2 over x multiplied by sine of 3x over 2 over sine of x. Now, to use the remarkable limits, we introduce the factor 3 over 2 so that sine of 3x over 2 takes the form sine of something over that something. Working carefully, we arrive at L1 equals 2 multiplied by 1 multiplied by 3 over 2 multiplied by 1 multiplied again by 3 over 2. This finally gives 9 over 2, that is 4.5. Teacher's tip: it is crucial here to manipulate trigonometric identities carefully and not to forget to introduce the right factor in order to apply the remarkable limits. Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow. Second question, calculation of limit L2. We now consider the limit as x approaches 0 of the following expression. The numerator is tangent squared of 2x plus sine squared of 5x, and the denominator is x squared. Once again, as x approaches 0, both terms in the numerator tend to 0, and the denominator also tends to 0. We therefore have an indeterminate form of type 0 over 0. Pedagogical reminder: there are two remarkable limits that are very useful here. As x approaches 0, tangent of ax over x tends to a. Likewise, as x approaches 0, sine of ax over x tends to a. Using these results, L2 equals the limit, as x approaches 0, of tangent of 2x over x all squared, plus sine of 5x over x all squared. Applying the remarkable limits, we get tangent of 2x over x tends to 2, and sine of 5x over x tends to 5. Therefore, L2 equals 2 squared plus 5 squared, that is, 4 plus 25, which makes 29. Teacher's tip: here it was not necessary to go through identities. It was enough to know the remarkable limits of sine and tangent. Question 3. Calculation of limit L3. We now study the limit as x approaches positive infinity of the following expression. The numerator is x squared minus 5 times sine of x, and the denominator is x squared plus 1. Pedagogical reminder: remember that the sine function is always bounded between -1 and +1. This implies that -5 is less than or equal to -5 times sine of x, which in turn is less than or equal to +5. Adding x squared to each part gives x squared minus 5 is less than or equal to x squared minus 5 times sine of x, which is less than or equal to x squared plus 5. Dividing through by x squared plus 1, which is always positive for any x, we obtain the following bounds. X squared minus 5 over x squared plus 1 is less than or equal to x squared minus 5 times sine of x over x squared plus 1, which is less than or equal to x squared plus 5 over x squared plus 1. Now the limit of x squared minus 5 over x squared plus 1 as x approaches infinity is equal to 1. Similarly, the limit of x squared plus 5 over x squared plus 1 as x approaches infinity is also equal to 1. Application of the Squeeze theorem, also called the sandwich theorem. Since the function being studied is squeezed between two functions that both tend to the same limit, it must also tend to that same limit. Thus, L3 equals 1. Teacher's tip: as soon as you see sine or cosine multiplied by a constant factor, but with no growth stronger than polynomial, think immediately of the Squeeze theorem. Dear students, thank you so much for watching this video all the way through. I'll see you again very soon for another session. Until then, take care and goodbye.